Okay, so now, as I promised, we're going to look at some ways that we can streamline this process a little bit. So we've got an example here where we want to find the derivative of each of these two functions. And these are similar, yet significantly different at the same time. So the first one, you've got sine of x squared. And so x squared is the inside function, and sine is the outside function. Let's do that one first, and then we'll come back to the other one. So the first thing I'm going to do is I'm going to actually rewrite this function because I want to space things out a bit and add to it just a little bit. So I'm just going to spread these brackets out just a little bit because I want to make some doodles on here. So think about it this way. You're trying to take the derivative of this function, and the first thing you're going to see, if you look at the outer layer first, the first thing you're going to notice is sine, right? And you might think, well, I know how to take the derivative of sine of x, but this one has x squared inside. It's not just sine of x, it's sine of x squared. So what do I have to do to account for that? Well, here's what you have to do. And it helps to imagine. I don't know if you wear, depending on who you are, you might wear glasses. If you do wear glasses, then imagine what it feels like to take your glasses off and everything gets a little bit blurry. So imagine that you're doing that. And if you don't wear glasses, well, then imagine you put someone else's glasses on and things get a little bit blurry. So it's the same idea, right? And this inside function here, this inside function of x squared, I'm going to point that out, that's the inside function, that's important here. If your vision's getting a little bit blurry, you might just not notice that inside function at all, and you might mistake this and think that this is just sine of x, right? So pretend you did that. Pretend your vision got worse for whatever reason. You took your glasses off, or you put some fake glasses on, and you got bad vision, and then you mistook this for simply just being the function sine of x, and you got excited because you thought, oh, great, well, if it's sine of x, I know how to differentiate it. The derivative of sine of x is just cosine of x. Okay, so what would that look like then? So I'm going to do y prime is equal to cosine. Except here's the thing, I'm not going to just say cosine of x, I'm going to say cosine of x squared, because that bubble that I drew around the inside function of x squared that you would theoretically have just mistook for just an x, you're also going to copy that as your inside variable over here. Okay, so that's the idea. You made a mistake. You thought this was just simply an x, so you took the derivative of sine of x and got cos of x. Except, of course, you copy whatever's inside here, you copied it as well. Okay, but then now imagine that you put your glasses back on, and or whatever happens, your vision goes back to normal, and you think, oh man, I made a mistake. I didn't even notice that, but there's a whole another function inside. There's a function x squared inside. I didn't notice that. And then you might think that you have to start the whole problem over, but you don't. The good news is the chain rule says that's okay. You can fix it. You just need to multiply by the derivative of the inside function. And that is all there is to the chain rule. Okay, so let's just go through the part. Of course, I still have to take the derivative of this. I still have to do a little bit more work, but the initial application of the chain rule really is that brief. The rest is just figuring out the smaller derivative and cleaning things up afterwards, and then it will be done. But before I do that, let's just go back and just recap on what the two main components are. There's two things being multiplied. Cosine of x squared, right? So what is that? That's the derivative of the outside function, differentiating sine, which gives you cosine, but the inside function gets left alone completely. But then its derivative gets multiplied on after, and by it I mean the inside function. So you multiply by the derivative of the function that's on the inside afterwards. Really, what you have here are these two pieces, right? The cosine of x squared, that's this f prime of g of x. It's the derivative of the outside function, right? We differentiated sine to get cosine, but the g of x is left alone. That g of x is equal to x squared, that gets left alone inside. Except now, it gets its derivative of the inside function, g prime of x, that gets multiplied on after. So that's where this is showing up. It's showing up here. Okay, so that's the idea. Let's finish it off now. So this is really just equal to 2x, right? Derivative of x squared. If you use the power rule, you get 2x. So really what you end up with is just 2x times the cosine of x squared. So that is y prime for part A. All right, well, let's try it again for part B. Then we can just use the same approach. So for part B, well, I'm going to do the same thing. I'm just going to write out the function we've got y is equal to sine squared of x. And it's helpful to actually, this is the standard way to write sine squared of x, but really what it means is sine of x all squared. And based on what we're doing, I really want to exaggerate which function's the inside function and which function's the outside function. So I'm going to take a moment to actually just rewrite this in a different form. I'm going to write this as sine of x all squared, because that's what it really means. And then if I do that, it's a little easier to identify what the inside function is. In this case, our inside function is sine of x. Okay, so I guess I've already written inside function up here. Let me just draw an arrow down here just to emphasize that. But now we want to take the derivative of the function y. So we want to find y prime. So how are we going to do it? Exactly like what we did last time, right? Pretend this was just an x and ask yourself, what would you do? Right? It's a whole inside function of sine of x, but pretend it was just x inside here and you just had x to the power of 2. How would you tackle it? Well, you'd use the power rule. Right, you differentiate x squared and you get 2x using the power rule. So now we'll use that to write down the first factor of y prime. Except we don't just have an x in here, right? We have sine of x. So the first thing what we're going to write down is 2 times sine of x. Right, so you start off by just doing whatever you would do if there wasn't an inside function. Okay, so that's the derivative of the outside function, but the inside function, which I've circled in a hyphenated green bubble, is left alone completely. But now, just like we did in the previous example, we multiply by the derivative of the inside function. We're going to do that here now as well, except this time our inside function is sine of x. So we're going to multiply by the derivative of sine of x. And now this time, well, now the only derivative we have left is this one over here, and it's just sine of x. Well, we know the derivative of sine of x. It's cosine of x. So what we're going to get is 2 sine of x times cosine of x. And actually, that's actually a double angle identity. That's actually, you can express this as sine of 2x. So that's another way to write that. And of course, that's optional. You don't have to change that form. There's nothing wrong with just leaving it as y prime is equal to 2 sine of x times cos of x, but I'm going to choose to take advantage of the double angle identity for sine and just write this as sine of 2x. So that's the more streamlined approach for applying the chain rule. We could have done both of these problems in the same way we did this one, and some people might prefer to do that, especially when they're first learning the chain rule, and I 100% support and encourage you to do that. The main difference being that in the previous page we actually took the time to write our composition function as an explicit composition and actually specify what the inside function was, and we specify what the outside function was, and then we actually wrote out carefully literally the chain rule happening, which is what happens at this stage, right? You can do that as well. But if you want to cut down on some of the notation, this is the streamlined approach. Okay, so there's many consequences of the chain rule, but I'm going to write down one here that shows up so often that it's worth taking special note of, and this is called the generalized power rule. So here's how it goes. If you have some constant real number n, and some differentiable function g, remember that just means that the function you can take its derivative, it has a derivative, then the chain rule implies the following. If you are encountering the derivative of some power of the function g of x, so really, remember n is some constant, and g of x is a differentiable function, so we've got g of x and we raise it to the power of n, and we want to take the derivative of that function with respect to x. Well, this is just a special case of a composition. Really, this is just nothing but a composition, like we have here in the statement of the chain rule, in the specific case where your outside function, little f, is just defined to be f of x is equal to x to the n. And if you make that, if you consider that special case for this formula here, what you're going to get is exactly this. So let's write out what the chain rule would give us in the special case where we have when our outside function is just a power function. That's another way to say this. Okay, well, let's just do exactly what we did up here. Let's just draw a bubble around the inside function. So that's g of x, right? And then we'll just take the derivative in the same way we did the previous example. So remember that there's two parts to the chain rule. First, you differentiate the outside function, but leave the inside function alone. So what's that going to look like? Just ask yourself, what would you do if everything inside the bubble, this green bubble that I drew, was just simply x? Then what would you do? Well, it would be x to the n. Then the power rule says the derivative would be n times x to the n minus 1. So you're just going to go n times g of x to the n minus 1. Because g of x was your inside function, right? You still are going to copy your inside function with you when you do that. So that's the first part of the chain rule. It's the derivative of the outside function with the inside function left alone. But then afterwards, you're not quite done. You're going to multiply by the derivative of the inside function afterwards. Okay, so if you were to compare this, again, with the chain rule, the formal chain rule here, this n times g, let me slide this up a bit so I can get them both on the screen at once. This n times g of x to the n minus 1, that's really your f prime of g of x. It's the power function differentiated, but the inside function left alone, right? And then of course this g prime of x is just coming straight from the chain rule formula. So this is called the generalized power rule, and it's really just a special case of the chain rule. But it happens so often, it's worth thinking about as a separate rule, I think. So this is the generalized power rule. You can add that to your formula sheet if you want, or just adding the chain rule is enough, I think. You just can't help but memorize this one if you use it enough. So let's look at an example right here where we use it. So we've got composition. We've got a function y of x, and it's written as a composition where the inside function is x cubed minus 1 and the outside function is 100. So really, it's like this formula where g of x is equal to x cubed minus 1 and your n is equal to 100. So in this case, our derivative, and I'm going to use Leibniz notation here, dy dx, writing it that way just to give you a variety. So we don't always have to write y prime. We can write dy dx as well. And so let's write down the derivative using the chain rule. So or using the generalized power rule, right? So we got our exponent of 100. We're going to bring that down in front like we have here. So we'll have 100 times x cubed minus 1, our inside function, because x cubed minus 1 is like the g of x here. So we're going to have 100 times x cubed minus 1 to the 100 minus 1. So we're going to start by going 100 times x cubed minus 1 to the power of 99. Right? That is just this piece right here. But then we have to multiply by the derivative of the inside function afterwards. So let's write that down. And I'll take a step to actually apply this rule, but I won't actually take the derivative of the inside function just yet. We can do that on the next step. And then, so what are we going to get? We'll get 100 x cubed minus 1 to the 99. This won't change. On our next step, we'll have 100 x cubed minus 1 to the 99. But then here, we're going to take the derivative of x cubed minus 1. So derivative of x cubed, that's the power rule. Just use, you're going to get 3x squared. Derivative of negative 1 is just 0 because it's a constant. So we're just going to multiply this by 3x squared. Okay, and then if I clean this up now, I can combine the 3 and the 100 to get 300. And then if I write the x squared out in front, I'll get x squared times x cubed minus 1 to the 99. So that is your dy dx in this case. So that's just an example of how you can apply the chain rule when the outside function happens to be a power function. And let me just emphasize one more time, you don't really need this rule. You could completely scratch this rule out and forget about it. As long as you remember the chain rule, that is enough. You can always recover it from the general full chain rule. So you don't, if you like to just keep your list of rules as short as possible, then you don't actually need this one because it's really just a specific case of the chain rule.